Oy, went from one Zoom meeting to another. Oh, I had a meeting for this our state organization of community college math faculty. Exciting. I got elected the president, but for next year, so I could leave the meeting this year. All right.
That sounds exciting.
Yeah, super exciting. Let's see, share my screen. All right, what is the plan for today? What are we even doing? We are probably going over homework questions, right? Oh no, not homework questions. 17.3, right? 17.3 questions. Even though we're not collecting that homework, you might have some questions about it. And then we've got some practice prepared kind of on future stuff. And then tomorrow we'll do some review on all of the stuff here. If you haven't yet, I've got a list of questions kind of up like we did before. So I have like all of chapter 16, all of chapter 17, just a bunch of problems from the exam review that's in the textbook. And so tomorrow we can work on some of those. Obviously, there's some stuff in there that won't be on the test, and so we can talk about that. Some of it you should be able to just click on and recognize if you open up the chapter 17 one, for example. You should be able to recognize, oh, there's a field here. Here's right here, matching the vector fields, find a potential function. Then there's going to be some line integrals here, right? Line integrals along this path. So there's definitely stuff that you'll recognize here as we go. And then there's stuff later on that will be like determine if they're conservative. We've done that. There's stuff later on that's going to be, there's Green's theorem, right? Use either form of Green's theorem. Well, nope, not yet. We'll do that one later. So unfortunately, I don't have it all broken down by section. It's just the whole chapter, but we'll kind of pick and choose, and we'll do that. We'll do some review, not tomorrow, sorry, that's Thursday. We'll do some review Thursday. Today, we'll start with some homework questions if you have some on 17.3. And then however much time we have left after that, we can work on some Green's theorem and divergence and curl from 17.4. And I think, did we do all the 17.3? Yeah, we did, right? So we already did all that practice last time. Okay. Oh shoot, I was gonna go outside and have class outside. Do they have class? Like sit out on my patio, but then I forgot because I got distracted by my meeting. So I'm stuck here in my office with my green screen. I tried to do a little more like professional background here, like with some math stuff on it. So looks a little more, I mean, the bulldog, or not the bulldog, the Sparta cat wasn't bad, but I guess I always like to start with questions about the plan. Anybody have any questions about timing, about what's going to be turned in, what you should be working on, exam, grading, any questions like that? Oh, you're still, why can I not hear you? I heard Rudy earlier. You're unmuted. Did my battery die? Nope. My headphones have battery.
Testing 1, 2, 3.
Yeah, see, I can hear Rudy. I don't know, Max. No. And it doesn't say you're muted either. I don't know.
Try making sure your headphones are plugged in all the way.
Yeah, is your headphone plugged in all the way? So that happens to me where I can hear, but I can't speak. Nope. You're going to have to use sign language. But I've forgotten all the sign language I knew.
Or just type.
Yeah, you're going to have to use the chat. I'll open up the chat. Sorry, man, that's a bummer. Yeah, we'll do the same. We'll do the same due date. What that means, by the way, is no offense, I'm probably not going to work all weekend. So since the deadline isn't until Friday at 11:59 p.m., it's probably going to be like the next Tuesday or Wednesday or something before you get that one back. So I'm trying to like keep my own mental health and not be working all the time. The videos are what kill me because they take like, 20, 25 minutes to record, and then I'm like made the poor decision of starting to make them fancy. And so now I feel like I have to keep making them fancy because it looks cooler with like the background and like, so they take like an hour to do for each one. So that means that the grading will not get done right away. But yeah, Friday at 11:59 p.m. for that. Mhm. Cool. Any other timing? Do you have any? Oh, no homework. Nope, no homework due this week. So the 17.3 is just going to be homework that you should be working on for practice, but it will not be collected. Our last homework assignment, we'll do 17.4 and 17.5 due next week. And then the 17.6, 17.7, 17.8, you should be working on those. But those will just be, we'll have like 1 or 2 questions from those sections on the final. They will not be, we won't have any collected homework from those. So we're just kind of off of our schedule. So it is what it is. Good question, John. Any other questions? Timeline? End of the semester? I feel like we are like in the stretch run here. Limping there, but we're in the stretch. All right. Okay, let me know if you do have any other questions. And by the way, I don't know, like some of my colleagues have been having these like video chats with students, like office hours. And I don't know, like I do have some free time during the day. So if you ever want to just chat about something and you don't want to ask here, or you think of it and it's Wednesday and we don't have class till tomorrow, you can shoot me an email and we can do like email, try to figure out via email, or we can do a video chat where I share my screen with you and show you how to do stuff. So don't be afraid to ask about that too. All right, let me open up the 17.3 homework. Too many windows open here.
I got a question on 15. If
15?
Yep.
Okay. All right. Let me get that up here. 17.3. Did we have the my life is just like blending together. Did we have the talk about the fall semester going online too?
I don't think we did.
Yeah.
No, I don't think we did.
It's not certain, but I feel like it's, I don't know if you probably don't remember what I was saying before we left. I'm like, well, it's not certain. I've heard people talking about it. Like this is like, the second week in March or whatever. We were wondering if we were going to close. And so I feel like that right now, where like my dean is asking us to form a committee to plan for online courses for the fall in case they make that decision. And the VP has said, we're thinking about fall. We're going to make a decision. So like it's totally in play. I'm going online in the fall. So yeah, but I don't know. I hope they make that decision, early so people can come up with good plans. 15, you said, Rudy, 15?
Yeah, 15 on 17.3,
3, right?
4.
Oh, 17.4.
Yeah.
I am in the wrong section.
My bad. It's page 1134.
Yeah, I don't have pages in my ebook.
Okay.
I just have like individual files. It's kind of nice. But then the page numbers. Oh, getting started. Suppose C is a boundary, compute two-dimensional Perl. All right, this one?
Yep, that's the one.
All right. Let me grab it. Any particular, like a multi-part one here, any particular part of it, or you want to just start from the beginning? Whoa.
I got A pretty good. It was B where I was stuck, and I feel like maybe I just need to review parameterization because I feel like that's always where I get stuck in.
How to parameterize it?
Yeah.
This paste so weird. Won't let me resize it. Oh, I don't understand. Sorry, like technical issues, like nothing like watching someone else. Look at the corner, like you see how like it's not giving me the like bi-directional corner. There we go. So weird. Good enough. Okay. Parameterization, good, okay. So it looks like it's given us the region here. That's kind of a weird way to describe it. X squared is less than or equal to y, which is less than or equal to x, which is less than or equal to 1.
Yeah, and that's what's kind of throwing me off.
Right. So y is less than or equal to x squared. No, greater than, or sorry, I can't read. Greater than or equal to x squared. And then y is less than or equal to x, and x is less than or equal to 1. So that means that this bottom curve must be y equal x squared, and the top curve must be y equals x, because y is above x squared and below x.
So like I just said x equal to t and then y equals t squared.
Yep, so
Okay.
R1, that would be exactly it. Once, if you have y as a function of x, you just let x be equal to t, and then let the y be whatever y is equal to, so t squared. And then t goes from 0 to 1 for that one, because they intersect over here at 1, 1. And then R2 of t, you don't need, you're not going to write one integral, so your t doesn't need to progress. You can like restart. And so I would just do t, oh, but I need it to go, ooh, okay, this is, does anyone know why I like paused there?
I gotta win with Ethan.
We're celebrating Fortnite wins here.
Duo squad.
A duo
squad.
A dual squad win.
We lured our
Okay.
teammates to the
I gotta go to
agency,
class,
and then
Bart.
we went to the shark.
All right. So does anyone know why I was gonna just do t, and then a 0 from less than t less than or equal to 1, and then I stopped myself. I was like, oh no, oh that's not good. Do you know why? I'll give you a hint. It's one teeny tiny little symbol that makes that incorrect.
Is it the less than or equal to?
No, good thought. Is this right here. The problem is the orientation. You see, if I do t, and t goes from 0 to 1, that's going to go from 0, 0 to 1, 1. It's going to go the other way. And we need it to come down. So
That should be
that,
from 1 to 0.
no, I mean you can't do your t values backwards.
Would it be like t negative t?
Good thought. What I would do is do 1 minus t. Negative t will give you negative y values, so that doesn't work. But now if you do 0, 1 here, sorry, 0 to 1, now when t is 0, it starts at 1, and then when t is 1, y is 0. So now it works backwards. Now it has the right orientation. So that was a little sneakier than it looked, just to get that right orientation. And I think it's interesting, you know, Rudy was thinking like, well, you could go from 1 to 0, but it doesn't really make sense to say 1 less than or equal to t less than or equal to 0. Like that's actually impossible. That's a contradiction. Because you're saying 1 is less than or equal to 0, which is not true. But the funny part is if you did that and you do your integral, it might work. Like it might work, it might give you the right answer, but it doesn't really transfer well, and it's kind of using poor logic, even though like it feels like it should work. I'll just reverse the t's, but you can't like go backward in time. And so even though it might work in the integral itself, it doesn't really transfer to other contexts well. So it's better to do one that will always work. So this little trick to do the 1 minus, or that idea of, I think Michael had a good idea, we're doing minus t, something like something minus t will kind of give you that, it'll reverse the direction for you. So those are the two parameterizations. Does that help with that, Rudy?
Yeah, that actually makes it a lot more clear.
Okay. And then the rest, you're just computing line integrals, which you could do right now. That's 17.3. That could be on this test. We won't do the double integral though, but we will for the final. Like that, this would be a good final exam question where, I don't know, it might be kind of long. I don't know, but it's something where you do both. We talked about this, where you do both the line integral and the double integral and show that they're equal. And same thing in D, you're going to do the two-dimensional divergence and then use the flux form to explain why the outward flux is 0. So that's the flux form of Green's theorem. There's two forms, the circulation form and the flux form.
Can we do part A, the curl?
Mm-hmm. Yep. So let's take a look. You got your formula sheet started. Go 17.4. Scroll up here. So the curl is the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And if you get 0 for that, it means there's no rotation in the region. The vector field is irrotational there. We'll need to do the curl is the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And then my f is up there. F equals 1x. So let's see here. The partial derivative of g with respect to x. So that'll be the partial derivative of x with respect to x. That's the g. Minus the partial derivative with respect to y of f, so that'll be a partial derivative of 1. And that'll be 1 minus 0, that's 1. So no, it is not irrotational.
Okay, yeah, because I was getting confused. Like, I was like, is curl like integration, or is it just like that part of the, you know what I mean?
So the curl is just that thing. And then when you compute, you get a net curl if you add them up and do the double integral. But the curl itself is just that expression. You can think of the curl of a vector field is some function, I don't want to use f, like some function, I don't know, a, of x and y. It's going to give you a function of x and y. It's going to give you the rotation at a specific point. And so if you get that that's always 0, it means there's no rotation. At any particular point, there's no rotation there at that point if that curl is always 0. Good. Any other homework questions? I've got 17.3 up also, which will be on the test for Thursday. I'm having a unique experience right now. I feel like I made a mistake wearing pants today. It's like really hot in my office now. It's like 70 some outside and I'm suddenly getting very warm. But no, I will not. I'm not going to change that situation right now, even though you can only see my top. That would not be good. There are all these horror stories of people like getting up and then showing more than they intend to show. That will not happen here.
I actually did have one on 17.3. I forgot about until just now.
Yeah, it's all good. All right, I've got it up here.
It's 45.
All right. Okay. Get that one in here. See how big it pastes on me. Oh, I really don't understand. Somehow I need to figure out, someday I need to figure out why it's pasting so big. It's something about the resolution. Almost. Okay. So we're going to evaluate. This is the notation we talked about yesterday that we just kind of threw in here and we haven't really talked about in depth. Gosh, let me keep going. Jeez, finally. This, the integral with the circle on it, that means it's a closed integral and you can see that C is a circular path. So it's going to go loop all the way around and end up back where it started. Now evaluate that for the vector fields in the closed curve by parameterizing C. If it is not 0, give an explanation. So any particular part of this, is it the parameterization or like anything particular?
Yeah, it was the parameterization again.
Yep, let's draw it here. Circle of radius 4, centered at the origin, oriented, this is important, oriented counterclockwise. So what I think about, I always reference back to the unit circle. In a unit circle, you can just parameterize by using cosine t, sine t. Right? X is the cosine and y is the sine on the unit circle. And that one starts out here on the x-axis and moves counterclockwise. And that's the one we're familiar with. So what I do is I use that as my basis. So any other circle, I say, well, does the orientation match? Do I need to switch the orientation? Switching the orientation is as simple as switching the x and y. But here I want it to be counterclockwise, so I am counterclockwise, that's fine. I don't have the right radius though, I have a 4. So all I'm gonna do is just scale the x and y, just make them 4 times as big. So this one, a parameterization of this would be 4 cosine t and 4 sine t, just scaling it out by a factor of 4. And then for the integral, that would be the integral. Let's see, one thing we missed was we need the interval for t. That would give us this full path. And we all know one time around the circle would be 0 to 2 pi. So it's 0 to 2 pi f. You turn f into the parameterization for cosine t, for sine t. Happens to be exactly the same, but that's because it's xy. So 4 cosine t, 4 sine t. Dot product with r prime, which will be negative 4 sine t, 4 cosine t, dt. And then continue from there. And you should get 0. But in fact, I knew we were going to get 0, and you could have as well. How could you have known that we were going to get 0?
The vector field's conservative.
Right, everybody remember that? So the partial derivative of f with respect to y is 0, partial derivative of y with respect to x, of g with respect to x is 0. And those are equal to each other. So therefore, our vector field is conservative. Now it did say compute the line integral, so you should do it. But here, when you multiply all this out, you actually just get 0 when you combine like terms. So Max, your point, it is only 0 if it's a conservative vector field. So even if it's closed, not every closed one will be 0. Yeah. The reason why it's closed if it's conservative, if you remember, if f is conservative, it implies that f is the gradient of some phi function. So then when you integrate over a curve of f dot dr, you just get phi at the end point minus phi at the beginning point. But if you're integrating over a closed curve, the ending point is the same as the beginning point, and so you get 0. But that's only if the field is conservative. So back up here to that one. Are we okay with 45, Rudy?
Yeah, that clears it up.
Okay. That's good. That was good. Any other questions? 17 I got 17.3 up right now, or we can do 17.4 also.
So if it's conservative, but it's not closed, what would it still equal 0 then, or
No,
no?
it might or it might not. So
Okay,
if
so
it's
that's just
not,
unknown then.
yeah, if it's not closed, then if you know it's conservative, you could use the fundamental theorem of line integrals and find phi and evaluate phi at the end point and subtract evaluating a phi at the beginning point.
Okay, but like if it were to like equal 0, would that just automatically mean that it's conservative?
If the closed, if
Okay,
only
so
if it's a
just
closed curve.
So they have to be closed and conservative.
Yeah, so those statements are equivalent. F, the field being conservative, is equivalent to saying the integral, the line integral over a closed path is 0. But that's only for a closed path.
Okay, got it.
Yeah, it's a good question, Max. I know we did a couple of those. So let's grab another one here. You see any that catch your eye in there? Anybody see one that looks good? We're going to try to, first of all, determine whether it's conservative. And then if it does, then find the potential function. So anyone want to try one here? I can just pick one, but no requests. Ty wants to do 28. What is D? Does it tell us what D is? Oh, it's a three-dimensional region. Yeah, duh. All right, so we're going to do this practice. We are going to do what Max said. First of all, we need to, I guess we should, we don't know if we're going to find phi because we have to see if it's conservative first. So one thing that throws people off here is this field doesn't look like a field, but what it's saying is x squared plus y squared plus z squared is all underneath that. So it's really x over x squared plus y squared plus z squared, y over x squared plus y squared plus z squared, and z over x squared plus y squared plus z squared. Ty, what are you doing to us, man? So we got to take some partial derivatives here. Okay, that's all right. So we're going to take the partial derivative of f with respect to y. That's the partial derivative here with respect to y. Now the nice thing is the numerator is x, so it's really, we don't have to do the quotient rule. You can think of that as x times x squared plus y squared plus z squared to the -1, because the y is the variable here, right? So it's negative x times x squared plus y squared plus z squared to the -2, and then we're finding the derivative with respect to y, so that's 2y. So it's -2xy over x squared plus y squared plus z squared squared. Okay, now we need to do a partial g with respect to x, and fingers crossed those will be the same. And then if they are, let's just assume the rest are all the same too. Let's see here. This is the same idea. Y times x squared plus y squared plus z squared to the -1. So negative y x squared plus y squared plus z squared to the -2nd. Then chain rule times the derivative of the inside with respect to x, mind you. So that's 2x. We get -2xy over x squared plus y squared plus z squared squared. Okay, excellent. Yes, that worked. So there are two other ones to check. We need to check, is the partial derivative of f with respect to z equal to the partial derivative of h with respect to x. And then we also need to check, is the partial derivative of g with respect to z equal to the partial derivative of h with respect to y? They're all the same format, so it's going to be yes for all of them. So we're just going to save ourselves a little bit of labor there to say, I'm going to just write them out here. H partial derivative of f with respect to z also equals the partial derivative of h with respect to x, and partial derivative of g with respect to z equals the partial derivative of h with respect to y. So therefore, our field is conservative. Okay. So what that means is there is a function phi of x, y, and z where our field is the gradient of phi. That's the definition of a conservative field. All right, I'm going to rewrite our field. I think this looks worse than it really will be. I'm hopeful, at least. Okay, so that's my field. That should equal the gradient of phi, which is the derivative of phi with respect to x, the derivative of phi with respect to y, the derivative of phi with respect to z. Any questions so far on the logic that we have so far? Oh, there we go. I know, sorry, I got maybe too small there. I was just trying to zoom out and show everything. Okay, I'm not seeing any hands raised or anything. Okay, so I'm just going to keep going. So now we're going to do this three-step process. We're going to start with, this means that the partial derivative of phi with respect to x is x over x squared plus y squared plus z squared. So then phi must be the integral of x over x squared plus y squared plus z squared dx. Does everyone see the x in the numerator and the x squared in the denominator? I don't know if you can see the u substitution that's going to happen there, and you're going to get natural log absolute value of u. But there, you're going to need an extra 1/2, and you can do the u substitution if you want. The 1/2 comes from when you take the derivative of the natural log of x squared plus y squared plus z squared, you get a 2x. So you have to balance that out. You can maybe try it off to the side for yourself later and do that u substitution, and you'll see where the 1/2 comes from. But here is the big key now. Yep, we have the natural log. By the way, I intentionally didn't write the absolute values there. Hopefully you were thinking, Professor, you did it wrong. You need absolute values there. But you would owe me a donut point because you actually don't, because x squared plus y squared plus z squared can't be negative anyway. So you don't need the absolute values. You can put them there, but they're unnecessary. So the big question is, what could have been added there? I know we've talked about it. Who wants to jump in? Max has got it. It's some function of y. I think we'll call it C1 of y or z. I think, what does your book use? I should just use the same thing they do. What's finding potential functions? They call it a C and then a D. Okay, all right, let's do the same thing they do. So we'll just call it C. Okay, because Max is saying that because we had the partial derivative with respect to x was the x over x squared plus y squared plus z squared. So there could have been some other function of just y and z hanging out there. Okay, so now phi is 1/2 natural log of x squared plus y squared plus z squared plus some unknown function of y and z. So that's step one. Step one, we start with knowing that the partial derivative of phi with respect to x is equal to the x component of my field, and then I get a phi. And so then now we do step two, we take the partial derivative with respect to y. That's 1/2 times 1 over x squared plus y squared plus z squared times the derivative of the inside, but it's with respect to y. That's 2y plus whatever the partial derivative of c is with respect to y. But see, we know from up above what the partial derivative of phi with respect to y is. It's the y component of the field because the field is the gradient of phi. And so very conveniently here, I don't know if you can see the simplifying, they're actually the same. So this means that cy must be equal to 0. All right, so now this means then that c itself must be, I guess we would normally say constant, but if the partial derivative of c with respect to y is 0, c could be more than a constant. Do you remember, anybody know what c could be equal to if its partial derivative with respect to y is 0? You can be a little more formal if you want. C of yz would be the integral of 0 dy. I don't know if that's helpful.
Isn't that just 0?
Kind of.
Just like an arbitrary constant, isn't it?
Close. You're closer.
Function of x.
Oh, parallel. So Ty and Max were saying z, it could be z, it really could be some function of z. Because any function of z, this is where your book is using d of z, any function of z, its partial derivative with respect to y would be 0. So it's some function of z. Okay, so now my phi, I've gotten a little more information. It's 1/2 natural log of x squared plus y squared plus z squared, plus now I just discovered that my c function is equal to, maybe it's not a function of y, it's only a function of z. And then we use the third prong. We haven't done the partial derivative with respect to z yet. Phi sub z, and you can do that work and you'll see it'll be z over x squared plus y squared plus z squared plus d prime of z. So you take the derivative of the natural log, you get 1 over the argument times 2z, but you already have the 1/2, so it ends up being z. And this is just d prime of z because d is a function of just a single variable, so we don't need the subscript. It's not a partial derivative, it's a single variable function. But again, we have the partial derivative with respect to z. It's right here. It's the z component of the field. So these are not very interesting, because what that means then is that d prime of z must be 0 So d, now tell me, if the derivative of this d function of z is 0, what must be true about the d function? Ty is right. It is a constant. That's correct. So now we're done. Therefore, my function phi is, where did it go? 1/2 natural log of x squared plus y squared plus z squared plus some arbitrary constant c. And you could put 0 there or whatever. It usually says, let me go over, I'll come back here. I'm going to just go over the instructions again. Usually says, notice the article here. Everybody good with their grammar? You know what an article is? Determine a potential function. It's an indeterminate article. It's not a determinate article. Whenever I think about that, I remember being in this Italian class I took years and years ago. And the professor was trying to do like the same, there's like the same thing in Italian about determinate and indeterminate articles and stuff like that. And I was in this class, I was older than them, most of the students. I was like 30 at the time. And I was with students mainly your age in their 20s. And they were so confused. They had no idea what she was talking about. Articles, what are you talking about? They didn't, they couldn't learn the Italian because they didn't know what an indeterminate and determinate article is, which is, I don't know why I remember that. That's not like I'm a grammar person, but anyway, the key is it says a potential function. So you could leave the c off and say, hey, c is 0. I have a potential function. Or you could put c is 18/7. I don't know, it doesn't matter. Any potential function is fine. So I don't know, I know we've done a few of these, and normally when we've done a type of problem 4 times, it's like, you know, you should be good by now. I just feel like this is a long process, and especially in steps 2 and 3, that's typically where people kind of lose the logic. So I think it's good that we asked about that. I don't mind doing that again. Any questions about 28? Any specific questions about 28? Max, that was your request to do something like that where you find a potential function. Does that feel better? Do you want to do another one? You good? All right. Anybody have another one you want to do there? Let's pull that up. Maybe we'll do, let's do are there any that are 2D? Maybe like, because I think they might be a little more interesting. Let's do maybe 19. Is that one assigned? It was, but that's okay. No, 17. Yeah, 17.3. That one was assigned. Oh, I don't know. Actually, I don't know if this is a good one because I don't know if it's going to be conservative. It might not be conservative. Let's see. Let's see here. We need to do the partial derivative of f with respect to y. Oh no, this is not good. That's negative x. Partial derivative of g with respect to x is x. Oh, all right. F is not conservative. Boo. It's funny how like this is not likely to be an exam question where it's determine whether it's conservative, and if so, determine a potential function. Because think about the amount of work on the one to find the potential function. And like, you know, that's a lot of work. You showed you know a lot of stuff, like that should be worth, you know, 10 points or something. Whereas here, you showed one fact. 2, you knew or had written down what it meant to be conservative, and you could take partial derivatives. Those are the 2 things you showed. And so I usually will separate those questions and have one question determine whether or not a field is conservative. And then another question, hey, here's a conservative field, find a potential function. And just kind of tell you that's conservative. All right, let's see if we can find one that is, I think 20 will be, 24 was assigned. Oh, I feel like we did that one or one really similar to that. That one's not conservative either. Yeah, so I think 20 will be. This is just, actually 20 is going to be the same thing, but only in 2 dimensions. I'm just trying to check these quick in my head. Let's try 26. Have we done that one yet? Looks kind of familiar. All right, let's see here. Oh, this one's not going to be conservative either. The partial derivative of 1 with respect to y will be 0. The partial derivative of negative z with respect to x is 0. Okay, so far so good. Partial derivative of, let me just write these, I guess, maybe partial derivative of f with respect to z will be 0. Partial derivative of h with respect to x will be 0. Okay, so far so good. Partial derivative of g with respect to z is negative 1, and then the partial derivative of h with respect to z is 1. Boo. Also not conservative. We're gonna do a modified 19 because I think all we had was the wrong, or well, here, let me ask you, Max. Is it the 3 dimensions that challenges you? Oh, h with respect to, oh, this is supposed to, yeah, sorry, this is supposed to be y. Sorry, I was kind of writing the right thing. Thank you, Michael. Is it the 3 dimensions that challenges you, or do you want to do, like, could we modify 19, or would you rather modify 26? All right, so how can we modify? I think all we need to do is make one of the z positive, right? So what if we did 1zy? I think that should do it. Partial derivative of f with respect to y, 0. Partial derivative of g with respect to x, 0. Partial derivative of f with respect to z, 0. Partial derivative of h with respect to x, 0. So far, so good. Partial derivative of g with respect to z, 1. Partial derivative of h with respect to y, 1. Okay, so with that slight change, now it's conservative. Okay, so since it's conservative, it is the gradient of some phi, and that means 1zy is equal to partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. We're going to have these 3 facts then. Partial derivative of phi with respect to x is equal to 1. Partial derivative of phi with respect to y is equal to z. And the partial derivative of phi with respect to z is equal to y. So we're going to use those 3 facts in our process. Okay, so if the partial derivative of phi with respect to x is 1, phi must be the integral of 1 dx, which would be x plus some unknown function, maybe of y and z. All right, step 2. Now we take its partial derivative with respect to y. We would get 0, and then I guess we just get the partial derivative of c with respect to y. But we know that is equal to z. Fact number 2. Well, that implies that c must be the integral of z. This is going to mess with you here, dy, because we were taking the partial derivative with respect to y. If your brains reflect anything like my brain, right here is suddenly where like I have to slow down and like it was really clear and then now it's fuzzy and I have to like, hold on, what is the logic here? So I don't know if you feel the same way, but it's because we were looking at the partial derivative with respect to y, so that undoing it, we have to do dy. What's the integral of z dy?
Isn't it zy?
Zy, yep, zy, because the z is a constant in this context, zy. And then there could be something else hiding out there, right? What else could be hiding in there?
Constant of x.
You're close. It's kind of like a constant.
Constant of y and z.
Closer. Max is not quite right either. You can't have a function that it can't be an x. We already dealt with x, we're done with x. All the x's were addressed in step 1. No more x's. Daniel's right. It's some function just of z. Just of z, because we dealt with the x's. We have all of our x's that we're going to have. If there were more x functions, they would have appeared in phi sub x. So there can be no more x functions. Okay, now my phi is x plus zy, or yz, I guess we'll do it in order, yz, plus maybe some function just of z. And so now we're going to use fact 3. The partial derivative with respect to z is just y, right? So phi sub z will be y plus d prime of z. You lose the x. Partial derivative of yz with respect to z is just y, and you get d prime of z. And that's equal to y. That's our third fact. And so this seems pretty similar to the last one now. This means d prime of z is 0. So d is just some constant function. It's not actually a function of c. So phi as a function of x, y, and z is now x plus yz plus a constant. Now, one nice benefit you have, unlimited time. So you have time to check. How do you check that you have the right potential function?
Take all the partials.
Right? And find the gradient and it should be equal to your field. So check the gradient of phi. Partial derivative with respect to x is 1. You lose the y, z, and the c. Partial derivative with respect to y will be z, and partial derivative with respect to z will be y, and that should equal our field, our modified field, right? We had to change the problem. So it checks. It's like a regular antiderivative. That's essentially what you're doing, right? It's just a 3-dimensional antiderivative. You have a field that you're trying to find. So this phi function is a little more challenging, but it's basically just an antiderivative, and you can check it by finding the gradient. Yeah, I think that was good. I don't know. I hope everybody found that valuable. I think that was good practice there. Any other homework questions? 17.3 our priority because that's what our test is coming on, but we can do more of those on Thursday. So either 17.3 or 17.4 and 5 would be fine. You're typing, Max? Yeah? Okay. I really wish it had, I should email Zoom. Like it would be nice if it had that feature, like so-and-so is typing. That'd be good. All right, so Max is good. Glad, that's excellent. I think what I'm going to do is I posted some practice if you want to try these. They are, oh, did I post? I did not post them on the homepage. Oh, sorry. They're under the content tab under Unit 5. By the way, these other optional videos here, they're not my videos, but the graphics are actually really good. My graphics are like my pre-printed notes or my pen, and they actually have like some graphics, some cool stuff about fields, and then especially the 3 blue, 1 brown. I don't know if you've ever seen them. It's a pretty big YouTube channel. A lot of awesome math videos. They did this divergence in curl. And it really, I think, is really helpful for you to understand what those two things are. So I have the notes. It's a single video. It's like 20 minutes or something like that. But this was it's a better introduction for the visuals. So, but that'll be something to do over the weekend. I'll remind you about those to look at those again. But I did post some extra examples there as well under the Unit 5 for the final. So we got about 10 minutes left. And let's do a couple of examples here. We haven't talked about Green's theorem today, so let me just write that up here. Green's theorem says essentially the line integral of a closed curve, I shouldn't say essentially, this is what it says. The line integral, which is the circulation, will equal the double integral over the region of the curl. Oh, wait, I need to do the right order. I always do this in the wrong order. I don't want to do it in the wrong order. So let me make sure I get the right one here. 17.4. Yeah, partial derivative of g with respect to x minus the partial derivative of f with respect to y. Should have trusted myself. That's all right. And so to Michael's earlier point, that on the left, the whole thing is the circulation. On the right, it's the integral of the curl. So the curl is a function. It's giving you like a rotational effect at a specific point, and then you're adding it up. So Green's theorem is this connection between what's happening on the outside and what's happening inside the region. So we're gonna compute the two-dimensional curl, but then part B here is most interesting. We're going to compare the two, compare what the circulation is on this path with what the curl is. So I don't know, we have 7 minutes left. We might need to go a little late. If you need to leave early, I'll post the replay. Sometimes these end up being a lot harder than you think. So let's see here. Let me draw a quick picture of our region. We have 0, 0, 1, 0, 0, 2. Here's our region. Find the two-dimensional curl of the field. That's easy enough. Curl is the partial derivative of g with respect to x minus the partial derivative of f with respect to y. Let's see, 3 minus -3, so that's 6. Easy. That's fine. That's just making sure you have good notes, right? You got the curl written down, you have the formula written down, you take some partial derivatives. B is the interesting part here. I think this is going to be a good example of the power of Green's theorem because I'm not really actually looking forward to the line integral. Does anyone have a suspicion about why I might not be looking forward to the line integral? C is the path along the outside, and we need some orientation here, by the way. We talked about this last time, how it's counterclockwise orientation. That's C. So C is that red path. So why might I not be excited about the line integral? I don't think so, Michael. Is it? I don't think so. Because the negative here, Michael is.
Oh yeah, I just mixed it up. I'm sorry.
No, it's all good. I like when I'm not wrong. You gotta appreciate those moments because the other side happens often enough. So I was going to ask about. We were asking about why I'm not excited about the line integral. The problem is you have 3 curves. So you're actually going to have to do 1 over, we'll call it C1 of f dot with dr. So you're going to have to parameterize that and then do that line integral and then add C2 f dot with dr and then add C3 f dot dr. Okay, so C1 R1 would be, let's see, I guess we can just go t and 0 and have t go from 0 to 1. Right, x goes from 0 to 1, y is always 0, and so we have our t from 0 to 1. That should work. C2, I have to go, let's see, what is, it's the line y is equal to negative 2x plus 2, right? Here's how we're going to do this. We're going to go t, then we're going to go negative 2 times 1 minus t plus 2. And I think that'll get us the right order. You'll notice, you see that little trick there? It's that same thing we did last time. It's more complicated this time, but this reverses the order. And I think that should do it. 2t minus 2 plus, just, that doesn't seem right. Shoot, I need to think more about that one. Because that doesn't, and t is, oh, I don't want to start at, no, I want to start, that's not right at all. So negative 2x plus 2, I want it to start at 0. That's what I want. I want it to start at 0 when t is 0. We need y to be 0 when t is 0, and then we need y to be 2 when t is 1. Can we just kind of eyeball that? Can we do 2 minus 2t? Nope. My brain is fried. So Daniel's right, like we don't need to, but we could. We could do either one. You can alter either one. You can make x and y whatever you want. Eventually you need an x component, you need a y component, and then you need an interval for t. Did you have a thought, Daniel? So what if we altered, I see what you're saying. So what if we did, yeah, so if I do t here, then I would have to start at 1 for my t. So what if we did 1 minus t, because that'll start when, if we do 0 to 1, that will fix the problem of starting at 1. So now it'll start at 1, the x will start at 1, and then end at 0. So that's a good idea. And then I think we should be able to do -2 times x 1 minus t plus 2. Now, does that work? Yeah, good catch, Daniel. I was so focused on using t as the x. Whoa, what is happening? So focused on using t as the x, positive 2t there, that I wasn't thinking about the x coordinate has to start at 1 and then end at 0. So I think this one works. Yep. Good catch on that one. There's my R2. Now that one works. When x is 0, or sorry, when t is 0, x starts at 1, and then when t is 1, x goes to 0. Sounds good. And then when x is 0, y is 0. When x is 1, y is 2. Whew, that was a lot of work. Okay, C3, R3 of t. Let's see, well, the x is always 0. And then the y, we kind of need it to go in reverse. Again, we need it to start at 2, and we could just do this. We could do 2 minus t, but then have t go from 0 to 2. All right, I was afraid of this. It is 3:07. I'm going to keep going because I think it's valuable, but I know you've already been here for an hour plus. So if you want to take off, you can just start the recording, pick up the recording after an hour, after the hour 5 mark or whatever. So I'm going to keep going though. So feel free to stay if you want. But if you got to take off, you got other things to do, that's fine. So double checking here, the first one, t0. T goes from 0 to 1, so x will go from 0 to 1. Okay, that one's good. Second one, we took some time, we figured that one out. That one should be good. And then third one here, we changed the range for t values, but that lets us do 2 minus t. When t is 0, y is 2. When t is 2, y is 0. So that pulls it down. Okay. Now, do you see why I was not looking forward to the line integrals? So now we're going to go back up to these line integrals. We're going to integrate from 0 to 1. The dot product was -3y. So -3 times 0 and 3 times x. Dot product with the derivative. I need to erase this here. All right, the derivative of r would be 1, 0 dt. Plus the second curve is also 0 to 1. -3 times the y, which was 2t. And then 3 times the x, which was 1 minus t. And dot product with r prime, which will be -1, 2 dt. Plus the third one, 0 to 2, -3 times the x is 0. Or no, the y. The y, we did the y, right? -3y. So 2 minus t. And then 3 times the x, so 3 times 0. Dot product with r prime, which will be 0, -1 dt. Man, at least the integrals won't be bad, but that is a mess. Anytime you see a piecewise and you're asked to do a line integral, your brain should just be like, no, because then I have to do like all these different parts. It's the only way to do it if you're asked to do a line integral. And this is going to show us the power of Green's theorem, by the way. That's why I want to get to the end to see the punchline, to see how easy Green's theorem makes it. It's way better. Okay, integral from 0 to 1, I believe it's all just 0, is it not? 0 times 1 is 0, 3t times 0 is 0, that's just 0 dt, so that one's gone. Integral from 0 to 1, negative 6t times negative 1, so that's 6t plus, and then we're going to distribute the 2 times the 6, so 6 times 1 minus 6 times t dt. And then the third integral from 0 to 2, oh, another 0. Negative 3 times 2 minus t times 0. And then 3 times 0 times negative 1, that's also 0 dt. Well, at least that was nice. Made our life a little bit simpler. It looks like all we have is the integral from 0 to 1 of 6 dt, which will just be 6. Wow. That was a lot of work for all those integrals to be 0. You don't know that they're going to be 0. The only reason they're 0 for this particular one is because of the specific field. If it was a different field, it would not necessarily, just because you're moving along an axis does not mean the line integral will be 0. It just is because of this specific field, that's why. Okay. We could explain why. That's an interesting discussion, but not worth it here. So now we're going to do the double integral over the region of the curl, which we did was 6, right? Partial derivative of g with respect to x minus the partial derivative of f with respect to y dA. We already did that curl, that's 6 dA. And so I think we should be able to do this relatively easily. Let's do dy dx. Y goes from 0. Well, you know what? This is easy enough. Let's not do a double integral. 6, the integral of 6 dA is just 6 times the double integral of dA. But what is the double integral of dA for any region?
The area.
It's the area. That's correct. This is just going to be 6 times the area of that triangle. That's 6 times 1/2 base times height. You get 6. Okay, this is me and my pen dropping it. That's pen drop. End of class. Green's theorem, so much better. Not always, of course. Sometimes the double integral might be better, but especially if you have an outer curve that's got a bunch of pieces to it, you can just find the double integral over the inside of the curl and you get the same thing. That's good. Now we're not going to have double integrals like of the curl over the region for this test, but that could be on it could be on the final. And here's a question I'm most likely to ask relevant to this particular question. I'm most likely to ask you to find the line integral over the region. Now you might say, like, dude, you just you couldn't even figure out the second curve on your own. Why are you going to ask us on the final to find the line integral? The point is, I need you to recognize, hold on, this is a closed curve. The region is simple and connected. I should use Green's theorem and not find the line integral like he told me. I should do the area instead. So that's the type of question you're likely to see on the final is, yeah, I'm going to ask you to do the line integral, but really, no, not even set up. No. I'm going to ask you to find the line integral. And you're going to do it. You ready? None of this. You're going to say, sucker, you can't get me. I know. Don't do the line integral. Do the double integral over the region of the curl instead. And that is the answer to the line integral. That is it. I'm just going to say find the line integral. I'm not going to say you have to do it with a line integral. I just want you to find the line integral. And so it's going to be important. This is what Green's theorem is. The connection I want you to make is if you have a closed curve and your region is simple, you have the option of, instead of finding the line integral, you can find the double integral of the curl, and that will give you the same answer. So that's the outcome that I really want you to get from that section. So that's what you're most likely to see is, I'm not going to say, hey, use Green's theorem here. I'm more likely to say, find this line integral, and I want you to know, oh, it's closed. I should see if Green's theorem works. Now, if it's a circle, it might be easier to do the line integral. Circles are pretty easy. We did that homework one. That wasn't too bad. So if it's a circle, maybe you just say, yeah, it's closed. I could use Green's theorem, but I'm going to do the line integral anyway. All right, it's 3:15. I'm tired. I'm going to go. Thursday, we will focus on review. We're going to focus on reviewing the chapter 16 and 17 practice. So you can come with some questions from that if you want to. We can do some more examples if you want. And then next week, I'm going to work this week on getting 17.6 videos up. Those are going to be really important. If you haven't watched 17.5, it's about divergence and curl, and those are important as laying, like those are big important definitions for the rest of the semester. 17.6 though is a big one. I was just kind of planning my videos for there. It's going to be at least 2, if not 3. It's a brand new topic. That's really the last big thing we're going to learn. So that'll be your task over the weekend. Okay. Enjoy the rest of your day. It's supposed to be a nice day. Got to mention, it's my birthday today. I'm not going to tell you how old I am. I'm looking very old with my gray beard. It's all right. I'm letting it grow. It's the coronavirus beard. So I will see you all Tuesday. Let me know if you have any questions. Thanks, Michael. Take care, everybody. I'll see you Thursday.